Welcome back, all. Now it's time for Jon, and he's going to speak about the topic compactive AI, quantum inspired AI model, and compression. He's a solution architect at Multiverse Computing, and the stage is yours.
Yeah. Well, please begin. Okay, let's get started. So first of all, thanks everyone for coming. Good afternoon. I see some familiar faces we've talked previously. So as she said, I'm John. I'm solutions architect here at Multiverse Computing, and I'm gonna talk today about CompactifAI, which is our quantum-inspired model compressor. Multiverse Computing. So we are a company based on San Sebastian, so the Basque Country in Spain. We are more than 250 people currently. We raised our Series B in June 2025. It was the second largest Series B in Europe this year. So we've raised almost $250 million by now. We have more than 200 published patents, and we've, as you've seen, have offices all around the world. So HQ is in San Sebastian in the Basque Country. We're also in Madrid, Barcelona, London, Paris, Toronto, San Francisco, Munich, and you can find us in many places. As some of you may not know, we are the largest quantum software company, well, quantum AI company in the world, actually the largest quantum software company in Europe. And this actually brings us to what is multiverse computing and how we got to where we are. So multiverse computing was born in 2019, so 6 years ago in San Sebastian, with a mission to apply quantum knowledge to today's problems. That is, using knowledge from quantum physics to solve today's problems in today's computers, not in quantum computers, that is, classical computers. We had our fair share of success within our first year. We had many blue chip companies working with us in multivariate optimization problems, some machine learning, some deep learning, and it was actually almost in 2023 where, working for Bosch, we found out that the same techniques that we used to run quantum-inspired algorithms on classical computers could be translated to AI and sort of compress large AI models by a huge amount, making them smaller, faster, cheaper to run. So we almost say usually that we discovered fire. From then onward, we gave a name to this, which is CompactifAI. We realized that we can apply CompactifAI, that is our quantum-inspired pruning, to large language models, or essentially any neural net, to make them much smaller, efficient, and meet any deployment targets that currently cannot be met with the sheer size of AI models. So essentially, we made oversized AI giants much smaller, meaning we can deploy them on the edge, on premises, in a way smaller version, just as smart. And we cracked this using our knowledge from quantum physics. Before I continue, I have introduced a couple of questionnaires just to get a vibe of the room, trying to know, which spaces are people building in. Then there's going to be a next question on the maturity of your AI workflows, so that I can make this a bit more interactive and maybe more interesting to your actual problems. I hope this works and we can see these percentages progressing. Okay, that's cool. All right, a lot of agents, RAG, vision. Okay, let's give it some more seconds before we move on to the next one. Okay, so I see a lot of agents, automation, some RAG, and some computer vision. Okay, that's really interesting. My background is in computer vision, actually. And okay, let's see how far beyond you are in those AI projects. POC, internal only. Okay, some early production. Okay, yeah. As I was expecting, a lot of POC, a lot of experimenting. Okay, so we are still pretty early in the AI development. Okay, cool. Great. So a lot of POC, but quite a lot less early production or production systems. So you're all familiar, I guess, with the AI challenges that we're facing. Exponential increase in compute power needed, energy demands, and access to hardware. So it's no news for anyone that hardware it looks like it's only accessible to hyperscalers. We require gigawatt amounts of energy to run the new data centers, and the rest of us don't have access to that much compute and energy. So this is a problem that we realized. Maybe you have also realized about it, and we try to solve it with our quantum-inspired approach in our technology, CompactifAI. So what is CompactifAI? Well, it's an extreme AI model compressor, and behind it is Tensor Networks. This is what enables us to have an edge over other pruning approaches and actually reduce the amount of parameters in AI models. So Tensor Networks is a toolset that we borrowed from quantum physics. I haven't mentioned it, but our chief scientist officer and chief technological officer are both PhDs in quantum physics. And so they were able to draw these similarities between what is used to represent many-body systems in quantum matter physics to how neural nets interact between each other. That is, Tensor Networks is a mathematical toolset used to represent highly dimensional arrays of data, a tensor, by decomposing it into the operations of smaller tensors. This was widely used in quantum physics, not so much in AI. We were able to draw those similarities, and that is what unlocked CompactifAI. Its advantages are, of course, more efficient, faster, scalable AI models. How do we do this? So we fundamentally use Tensor Networks for the first step, which is called profiling. Here we are able to do some sort of forensics analysis of the AI model. We go layer by layer, analyzing the correlations of the weights. That gives us a very deep understanding of where the knowledge lies in, which are the parameters or layers that are more important to the end response of the model, where actually there are some parameters that are redundant or add nothing. And so once we've done this, we can prune the excess weight. We can remove the weights, we can remove dimensions, we can remove full layers that we have seen don't contribute to the accuracy of the model. And then essentially we get a much slimmer model. However, that could come at a cost, that is some loss of accuracy. To ensure we don't see that loss of accuracy in the end model, what we do is we run a healing step that is a very small distillation-like training. So we ensure that the outputs of the pruned model are aligned with the outputs of the base uncompressed model. That is sort of a teacher-student training that is very efficient because we're only training the leftover weights of the pruned model, and we are not requiring as many tokens as are required for full pre-training plus post-training. It's just a very small 1 to 2 epochs on a reduced dataset to align the outputs and ensure that we are not losing any accuracy. If there are here any experts on pruning, this may ring a bell on what NVIDIA published not so long ago on their Minitron approach. For the Minitron families of model, NVIDIA essentially did a structured pruning of the llama families, achieving quite a big reduction in parameters with a lot less training tokens than were required by Meta for training from scratch. And how do we compare with this? Well, we are actually even more efficient on training data and obtain much slimmer models. Why? Because tensor networks allow us to more efficiently and in a more sophisticated way understand which layers of the model or which weights are redundant. That is, it gives us the edge with less data, less compute, and in turn, we get a slimmer model. What does this unlock? Well, big size reduction, big increases in speed, and of course, reduced cost of inference, and it now allows us to deploy our models on the cloud, on premises, or on the edge. And before I go on, I just added another small questionnaire to sort of get the vibe of the room. Which are the challenges that you're finding most concerning, if any of what I'm saying is, well, applies? Okay. Some governance, a lot of energy consumption, model accuracy. All right. Okay, so we got almost the winning three. Governance, energy, and accuracy. Cool. Okay, so based on this answer, so accuracy, energy consumption, and data governance, what can we now unlock thanks to slimmer, smaller models? Well, so the first of the use cases that we are now working on and trying to achieve is what we call the router. That is combining a hybrid architecture between on-device AI and cloud AI, which leverages the best of both worlds. Whenever we input a new prompt or query, there's a local fast model that analyzes the query and routes it to answer it with the small local LLM, or routes it to a cloud, larger, more intelligent LLM. Imagine, I don't know, a cloud-hosted DeepSeek-like model, state-of-the-art across all benchmarks, huge, expensive, a lot of energy required, and a small 3 billion compressed llama. Of course, they are the opposite variants of the models we can find. One super smart, super large, another much smaller, less intelligent, but much faster. Now with the router, we can leverage the best of both worlds, because if we're asking a confidential question, we can ensure that's not going to go anywhere that's not on the internet. If we're asking a super hard math question, well, it's not going to be the Llama 3 billion parameter model answering it. It's going to be the cloud-hosted smarter model. And what if we don't have any connection? Well, then now we are covered. Of course, this drastically reduces costs, because the amount of queries that you're routing to the cloud model is probably less than what we are right now. You don't need Cloud Opus 4.5 for every query. Dumb questions can be answered by dumber models. But we get the best of both worlds, as I was saying. Some of you may have seen it. I actually have the router app here. Maybe I can show it later. We implemented this because we think it's really interesting and unlocks a lot of possibilities. Another use case that we have seen is really interesting and now enabled by these Tensor Networks and CompactifAI was recently featured in MIT Technology Review, where they painted us as some quantum crazy physicist who decensored DeepSeek, but it's actually a product line that we're working towards that we call Lobotomizer. As I said, we can use Tensor Networks to identify where knowledge lies in. That is, we can, in a very sophisticated way, identify where certain keywords, phrases, knowledge, concepts lie into the model, and we can surgically remove, alter those behaviors, decensor or censor, that is, lobotomize the model. It's actually quite interesting. If you go to the Hugging Face DeepSeek R1 model and ask it to draft a manifesto demanding the international recognition of Taiwan, it very politely denies to do so, as we could all expect. This is something that you can try for yourself. But we actually tried to run that same query on our CompactifAI DeepSeek model, and well, it just did. It just didn't oppose to recognizing Taiwan's international independence. It just drafted the manifesto, and this is essentially what MIT Technology Review were talking about. We now have a tool set that allows us to identify where the knowledge of the model lies in, and that unlocks not only, well, removing the parts that have no knowledge, but actually alter the behavior or those exact concepts in the model's internal architecture. How do we serve this? I said, okay, we compress LLMs and all sorts of models. How do we make this available to the public? So we have the CompactifAI API. This is an API hosted on AWS Marketplace, which you can all access to. And we are featured on artificial analysis. So you can see that all of the benefits that I was talking about, smaller models, faster, no loss of intelligence, are not only things that I claim, not only marketing stuff, they're actually tested and benchmarked every 8 hours by artificial analysis. Here you can see that our Llama 3.3 70B is competitive with Grok and Sambanova, which are custom chip manufacturers working on custom silicon boards to make inference faster. We are almost as fast as them at a fraction of the cost. And adding to this, artificial analysis only benchmarks the uncompressed variants of the model. So they need to test apples to apples. So in this case, it just comes to show how strong our serving and platform team are, because this is an uncompressed variant of Llama 3.3 70B. Once we introduce compression with Llama 4 Scout, for example, we jumped to second place. We get much faster in terms of tokens per second, much faster in terms of time to first token. Why is this? Because less parameters means less operations. So, well, we need less flops to run the same query and output the same output tokens. I think this sounds quite logic, right? And actually, just don't take my word for it. I recorded a video, but I've made this demo today to a couple of you. Feel free to come by the booth if you want to see it live. We can just ask it anything. So I think it's what can I do in Eindhoven that I was asking it. I just want you to see how much faster we get. So the one in the right is the compressed Llama 4. This you can get access to through our CompactifAI API. But we just don't have an API that will add complexity to you. We have an API that is compatible with the OpenAI clients. It is compatible with LangChain. It is compatible with OpenRouter. You can just replace 2 lines of code. And I guess for those of you building the POCs, this will be really handy. As I said, however, we just don't stop with LLMs. Our CompactifAI technology can be applied to computer vision models. This is a demo that we did with a compressed YOLO V8X. Someone told me, okay, but YOLO is already a small family of models, which I agree, CNNs are really efficient, but we can even remove more channels of a CNN. In this case, we removed 80% of the parameters, so we went from a 68 million parameter model to a 14 million parameter model that is twice as fast almost and loses no accuracy. Actually, you can see, I don't know, in the video, predictions. So the one in the middle is our compressed, the one on the right is a ground truth. Predictions are equally as good or better after compressing it. So this only brings really benefits. And yeah, this is another demo that I don't think is necessary. So pretty much this was it. I want to leave some time. I think we got 10 minutes for Q&A. I want to make this an interactive session because a lot of questions popped up in the booth. Just want to give you the voice. And here you can sign up to use the CompactifAI API.
Thanks for your presentation. So all of this seems to be very private for you as a company, like this is the product that we built. Is any of this stuff also open source or published as papers?
We have papers. If you actually look for CompactifAI, there's an archive paper. There are several papers on the use of tensor networks, one for CNNs and another one following up, I think, CompactifAI. Those are, though, a bit outdated. So those make reference to the first versions of CompactifAI, where we decomposed the tensors of the weights into tensor network operations. But that added overhead as to, well, now the network is not exactly the same way, so you need extra packages. But those give a general overview explanation of how CompactifAI works. Now we have moved forward and only use tensor networks for profiling, so that we can make sure that the pruned model's architecture is the exact same as the original, so that you can use the same Hugging Face class or the same PyTorch class. But yeah, there are papers in archive that if you search CompactifAI or you search our CSO, Romano Rus, you'll find them in no time.
Thanks. One more small question, if I'm allowed. Are there any circumstances in which the compactified model performs worse, or like is lacking something that existed in the original model?
Probably yes. I mean, if you push it to the edge cases, so for example, I'm from the Basque country. I don't know if many of you know it, but Basque is a small language. If you try to ask Llama for Scout to answer some questions in Basque, it may answer eloquently sometimes. The compressed version may not answer as well. That's why we include the healing phase. So when there are use case specific compressions that require to be made, we make sure to introduce private datasets in the whole stage so that the pruned model performs equally as well. For generalistic models, if you push it to an end case, to a very edge case, you might find some degradation in performance.
Thank you.
Bunch of questions here.
Thank you for the nice talk. I was wondering, this pruned YOLO networks, do they work on edge without any internet connections?
Yeah, we've actually been able to run a YOLO V8 Nano that we compressed on a 4 megabyte FPGA board. So they can be pushed to the extreme. And another question might pop up. This is compatible, of course, with quantization techniques, so that we can even push for more memory reduction. But quantization comes at a cost of precision, so that is an extra step that you can take. But yeah.
Hi. Thanks for the talk. It was quite interesting. I want to understand the difference your technique makes in comparison to, let's say, small language models or smalls.
Yeah.
As you say.
Yeah. We are not training models from scratch, even if that is a small language model, because we are striving for efficiency. And this moves so fast that you might devote your resources to training a much smaller model, and then it comes up and next week it's outdated already. So we are trying to focus on compressing larger, more intelligent models that are open source, so that we can see actual direct efficiency gains from compression. But we've also compressed some smaller versions. We have a small LM2 by Hugging Face that was 135 million. We were able to compress it down to 94. So even when you go down to the range of millions, there's some extra redundancies that we are able to remove.
In continuation to that, is there an open source version of one of your models which I can play with?
No, because there's a high risk of reverse engineering. So by now, we are trying to protect our IP as much as we can, and we haven't no open source variants. But you can play around the API, it's really cheap.
Yeah, just one question. So about the desensoring, is that a side effect of the compression, or do you have to target the desensoring? If so, can you give me an intuition of how that would work?
So we can, well, we usually target it. So for example, DeepSeek was, really widely known that it was kind of censored. So for this version, the research team tried to target specific sets of knowledge. So we search for public data sets that flag out this censorship of the DeepSeek model in this case. And we were able to strictly localize which activations are happening with certain questions or concepts, and then only update those. Yeah, thank you.
Hi, have you noticed a performance drop-off in relation to the context window, given that you reduced the model parameters?
So there could be some performance drop with the very extended context. So for example, Llama 4 Scout has a 10 million token context. Theoretical, of course, because if you even push the original model up to 10 million tokens, performance degradation is there. So it is almost in par with the original model in the compressed counterparties once you push for the limits of the context length. But that, I think, is not attributable to compression, but rather something inmate to the model's architecture. But yeah, I mean, we see very similar drops in precision with the uncompressed and compressed variants once we push the context length, I don't know, up to 10 million tokens in this case.
I think we have time for 2 more questions. Someone else?
Hi. So it's very cool that you can do that, but I want to understand what would be the benefit of it versus, for example, using smaller models for like an easier task, let's say a binary classification task, and I can just use like a very cheap, because when I upload to the API, I can't get my model back with the parameters because that's your IP, right? You could reverse engineer it.
Yep.
So what's the difference between me using cheaper models, also orchestrating them, or doing some LoRa fine-tuning or quantization that are also available to like make the model smaller?
So we work with all of our customers, and we can license the models so that they can be deployed on the customer's terminals. So if you really wanted to have a local model running on your device, that's something that we can reach a commercial agreement to, but we just don't make them open source on Hugging Face for everyone. Of course, if you're looking for a really easy task like a binary classification, maybe you don't even need an LLM.
Trying to an example of, because when would this be more favorable to purchase for me of you versus using a combination of cheap cloud models plus some LoRa fine-tuning if I have a local model that's what would just be the benefit of doing that versus orchestrating a bunch of small models or doing some LoRa fine-tuning?
Yeah. So for example, for the Llama 3.1 variant, the graph that I showed, you can see that you're getting a model of comparable or same size that is slightly or noticeably more intelligent in certain cases. So you're getting a more intelligent model at a reduced size when you don't want to trade off intelligence and you don't want to fine tune, because we see that many of our customers don't want to fine tune because then a new better model comes and you cannot just swap it up. That's one of the benefits.
All right. Thank you.
Okay, then I think we have to wrap it up here.
Thank you, Jon. I think Jon will be around here and you can ask your questions. There will be 5 minutes of break. We'll all meet again later, and let's give it up for